So this topic is all about factoring polynomials completely. Now, in the past, we may have said something was, quote, not factorable. For example, let's go back to quadratics. In the past, we would have said, I'm just making this up, x squared plus 6x plus 1 is, quote, not factorable. In truth, what we really mean is it's not factorable over the field of rational numbers. However, we do have this very important theorem in the world of polynomials called the factor theorem. It states, if x equals some number, I'll use c, is a root, then x minus that number is a factor. In other words, if I know that x equals, say, -1 is a root, then automatically I know that x minus a -1, which is just x plus 1, is a factor. So what it says is if we can solve equations, we should be able to factor them. And of course, at least in the case of quadratics, we should know how to solve every single quadratic equation. So what does this all mean? Well, if we extend our number system to include complex numbers, square roots of negative numbers, and if we apply this factor theorem, that means that every single polynomial function should be able to be factorized into linear factors. Quote, not factorable should no longer be in our vocabulary. We just have to be able to factor and solve and then apply the factor theorem. So for example, suppose I ask you to factor completely, I don't know, x cubed minus x squared, or I guess I should write this as a function, factor f of x equals x cubed minus x squared plus x. Well, the first thing I want to do, since it said factor, is see if I can factor any GCFs. You should always try GCFs before doing anything. Well, clearly they have an x in common, so I know I can factor out an x squared minus x plus 1. And now all I have to do to answer the question, completely, that's important. After I factor out the x, now to answer the question, I need to factorize this guy. But he's not factorable by normal means. So I guess this is like on the side or scratch work here. I need to solve this guy. Again, the only reason why I'm going this route is because he's, quote, not factorable by normal means. Well, it's a regular quadratic, so hopefully we have skills by now to solve quadratics. Solve it by completing the square, solve it by quadratic formula. I think most of us are comfortable with the quadratic formula. So, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that gives us a 1 plus or minus the square root of 1 minus 4 over 2, 1 plus or minus the square root of negative 3 over 2, and what do you know, when you take a square root of a negative, you produce imaginary numbers. Now what I would like to do is I'll go ahead and split apart this answer into two because we sort of need it separated. Let's see, so we have 1 plus I radical 3 over 2 and 1 minus I radical 3 over 2. So those are our two solutions. So how do I factor the original polynomial? Well, according to the factor theorem, all I need to do is 1 minus this ugly answer, and that'll produce a factor. So going back to the left side, we can answer the question. So f of x equals that original x that we factored out times x minus one of our answers. So you literally just write what the answer is. I'm going to put it in parentheses though. 1 plus I radical 3 over 2 times x minus the other answer, 1 minus I radical 3 over 2. Now, believe it or not, as ugly as it looks, that is factored. You factored it. If you don't like the double parentheses, you could distribute the minus in. So that would be x times x minus 1 minus I radical 3 over 2 times x minus 1 plus I radical 3 over 2. I suppose that does look a little bit neater. But this or this I would accept. And that's basically factoring completely. Anything that's, quote, not factorable, just solve it like a regular problem. And then once you have your two answers, apply the factor theorem. So to factor completely, solve, and then rewrite in factored form. Let's do another one here. Say, oh, I don't know. Factor f of x equals x to the fourth plus 10x squared plus 25 completely. Well, first things first, we should notice that we're given a trinomial 1, 2, 3 pieces. Notice how this exponent of 4 is exactly twice as much as this exponent of 2, and the whole guy ends in a constant. So although he's not a quadratic, he behaves like a quadratic. So I can factor him using the same techniques. Whatever positions I put here will have to multiply to x to the fourth, and of course, x squared times x squared equals x to the fourth. Then whatever numbers I put here has to times to 25 and adds to a 10. And again, I hope that's pretty simple. That's going to be a positive 5 and a positive 5. Now, these guys right here is, quote, not factorable. But do note how they are two pieces. I'm going to sort of put a pause here. So let's put this in the back burner. So I guess I'm going to use a different color here. So let's say this is not scratch work, but as an aside. Consider, back early in the topics and early in the year, we talked about special factoring patterns. And one of the special factoring patterns is the difference of two perfect squares. We said that the difference of two perfect squares always factorizes in this particular manner. Now, in the past, we've only applied it to, well, perfect squares. But there really is no rule that says you have to use perfect squares. As a matter of fact, as long as you know the relationship between b squared and b and a squared and a, you can use it. And it's a very obvious thing. To go from a squared to a, you just take the square root. To go from b squared to b, you just take the square root. So, to factorize any binomial, you just take the square root minus square root, and then multiply it by the square root plus square root. That's what this sentence says. Square root, oh, you guys can't see that. Square root minus square root times square root plus square root. Now, here's the issue. This pattern only works for minuses. We have a plus here. Well, we just need to remember, note, that a squared plus b squared is simply a squared minus a negative b squared. Every single addition problem can be rewritten into a subtraction problem. So when you take a square root, you're just going to be taking a square root of a negative number, which will produce i's. But that's basically the idea. So let's go back to our problem here. We still need to factorize. F of x equals x squared plus 5, x squared plus 5. So now I'm going to do some scratch work here. I need to factorize x squared plus 5. Well, according to what we said, we know that that's x squared minus a negative 5. So if I want to use the difference of two perfect squares pattern, I know I'm going to have to do some square roots. Well, what is the square root of x squared? That's just x. What is the square root of negative 5? The square root of negative 5. Remember, anytime you take a square root of negative, you just pull out that negative with an I. So that's going to be a I radical 5. And then you just do the positive. So what we have here is x minus I radical 5, x plus I radical 5. And since this guy was the same, we'll just go ahead and factor him accordingly. There we go. We factored it completely. You can leave it all spread out like this, but most people notice, hey, if I got the same terms here multiplying, let's just use exponents, because we know multiplying something by itself is just squared. So we have x minus I radical 5 squared times x plus I radical 5 squared. So that would be the complete factorization of our original problem. So the moral of the story of this particular example is remembering this very important factoring pattern, and now understanding that we can utilize it even if we don't have perfect squares, even if we don't have subtraction. So what I want to leave you with is just remembering some other important ideas, other special patterns. Do know that we do have a factoring pattern for cubes. It says if you have a perfect cube minus perfect cubed, that's going to be cube root minus cube root times a squared plus ab plus b squared. You do have a pattern for pluses. So cubes, you don't have to do a special trick for pluses. It has its own special pattern. A plus b times a squared minus ab plus b squared. That's about it. Yeah, so factoring polynomials completely, it's just a matter of if something's not factorable, try solving it first. Or if you notice that your non-factorable thing only has two pieces, like an x squared plus 5, use some factoring patterns. Just go ahead and give this a shot. Practice makes perfect.